Hello guys, and welcome back to another video. So it's been a while, but today I wanted to talk about pendulums, and we're going to find the equation of motion of this pendulum in a particular way. We're not using this standard way, but we're doing it using torques instead, because they're very useful when we're talking about something that rotates. Yes, we're going to derive the equation of motion. So firstly, we have this pendulum hanging from the ceiling, and it goes back and forth, and we know our pendulum behaves. And this is the vertical from the point attached to the ceiling, and it is displaced by an angle theta. Now, we're talking about torque, so we need to choose an axis of rotation. And in this case, we're choosing this axis perpendicular to the whiteboard. Why are we using this axis? Well, because it's simpler, of course. We could have chosen this axis of rotation. We would have got the same equation at the end of the day, but it's a lot more difficult and complicated, so we're not going to do that. So now that we've chosen our axis, we need to find the forces acting on the object, because this is what Newton tells us to do. This is the art of Newtonian mechanics. So let's find what these forces are. So we first have this arrow here. This is, of course, gravity, because this pendulum, this mass hanged to the pendulum, is subjected to gravity. So this is m times g, the gravitational acceleration times the mass. Then there's another force here, and this force is characteristic to the pendulum, and it's the tension of the rope. Now this tension, I call this tension with the letter T. It's directed inward towards the axis of rotation. And there are some assumptions here to keep things simple. And because this is what we do in physics, we keep things simple. Otherwise, we could do nothing at all. So this rope is considered to be massless. Now, you might argue, why massless? Because this spring certainly has a mass. Well, because there's no need to consider the mass of the rope, because compared to the rope is so small, it's negligible. And there's another assumption, that this springs has a constant length. So if you just apply a force to the ends of the spring, it remains with a fixed length that we call L. L is the length of the rope. Now, of course, this is an approximation, but it's very, very useful. And okay, we can move on. Now we have the two forces, and we need to find the torque. So what's the torque? T. No, sorry, I call with T the tension of the rope, so let me use the letter M. I know this is a weird notation, but my textbook uses this notation, and it uses P for angular momentum instead of L. I know I don't like this notation, but it's just a letter. The concept is important, not the way we used to represent it. So we're sticking with this notation here today. So what's the total torque? Well, it's the sum of the torques, and we have the torque for mg and the torque for the tension. Now, we know that the torque is defined as the position in which the force is applied, and we take the cross product with the force itself. Now, what is this vector in our case? Well, it's the vector that goes from the axis of rotation to the mass m. So this is r, and I've drawn it here, but it should be overlapped here, but you get the idea of what's going on. So we are going to replace our force with mg plus the tension, and we know that we can distribute it, so we're going to do that, and we get R times mg plus R times the tension. Now, we are trying to find the torque around this axis of rotation, and we did it for a very specific thing, because this R cross T now is simply equal to 0. We don't care about the tension. We don't care about it, because since we chose this specific axis of rotation, we know that R and the tension T are parallel to each other, hence the cross product is 0. So we get a simpler equation for the torque, because there's no way to keep things complicated when we can simplify them. So what is this torque equal to? We can find this cross product. We know it is the modulus of R, and the modulus of R is just the length that we called L, times the modulus of mg, so times mg, and then we have to multiply by the sine of the angle between the two vectors. And what's the this angle here? So we can translate R here, because all in all these vectors should be at the origin, but we drew them around the whiteboard to illustrate what's going on. So we can simply move R here, and this is the angle between them. And as you can see, it's theta. So we have sine of theta. Perfect. And then we need to find what's the direction. So I'm going to call two vectors. This vector coming out of the whiteboard that I represent using this notation, because the whiteboard is two-dimensional. I cannot draw a three-dimensional vector here. It's called n, the normal vector to the whiteboard, to the plane, and the vector going in the whiteboard is simply minus n. So we need to find what direction we have to pick, because of course if the initial velocity is in this plane, then the motion, we all know that the motion of a simple pendulum is on a plane. So of course this vector is static, it's not moving, but we need to choose the direction. And we're doing this using our right hand. So we have R cross mg. So R goes in that direction, mg goes down. So we need to pick the vector minus n that goes in the whiteboard. You can do it in another way. You go to the vector R. Okay, this is a bit complicated. Then you turn your fingers towards the vector mg, because it's R times mg, and your thumb points in the whiteboard. So we need to pick the minus n direction. And of course, we can just bring this minus outside, so minus lmg sine theta n. And we're done, as you can see. Okay, guys, sometimes I'm just checking whether my camera is recording, my mobile is recording. Okay, now we need to find the equation of motion with this information, that the torque is minus mg sine theta in the n direction. And we're going to use a specific theorem, so that the time derivative, the time change of the quantity p, that for me, for my book at least, it's angular momentum. I know you prefer to call it L. I also prefer to call it L, but we're sticking with this notation today, equals to the torque And this is not always true. This is true only if the axis of rotation we choose is stationary in our inertial frame of reference. Otherwise, we need to add an extra term. But in this case, the ceiling is not moving in our inertial frame. So that's it. And okay, now that we have this formula, we need to find what this P is. Because we know that the angular momentum is defined as R cross the momentum, so the position relative to the axis of rotation, cross the linear momentum that I call Q. But we know that the linear momentum is the mass times the velocity, and now we know another very important thing. We know that the position and basically the vector that points towards the mass hung to the pendulum, hung to this rope, is always perpendicular to the velocity. In fact, the velocity goes in this way or goes in that way. Since the two are perpendicular, this cross product equals to the magnitude of the first one times the magnitude of the second one, and I need to use the magnitude of this is a very important point. I need to use the magnitude of the velocity times the sine of the angle between them, that since R is perpendicular to V, the angle between them is just 0. So no, sorry, it's 90 degrees. So the sine of the angle is 1 times the normal vector. Now, this normal vector here, we need to think carefully about this normal vector here. I'm going to call it n plus or minus, and I'll explain you why plus or minus. Because think about two situations. When the pendulum is in this position, it may be swinging this way and then it's going up. So it's going up in this way, and the velocity is of course in this direction. The pendulum is doing like this, it's going up right now. But after it has reached a maximum height, it goes back. It passes through the same position, but with the velocity in the other direction. So as you can see here, R cross V, this is R cross V, gives me the same magnitude, but in this direction. In this case, it gives me the opposite direction, so I have to choose minus n. So how can I write it in a very simple way? Well, we're using the sign of the velocity. Instead of putting the absolute value, if we have LmV, then this is of course in the normal direction here. Think about it. Here the velocity, we might call this the increasing velocity is in this way when the angle increases, of course. So when the angle increases, the velocity is positive, and it's indeed in this direction. When it's going the other way, well, the velocity is now negative, and of course negative in the direction pointing out from the whiteboard is of course in the minus n direction. So now things work, because at first I got confused about this, but then I realized it worked beautifully. So now we can go on. We've almost done. We have that the torque equals the rate of change of the angular momentum. This is the angular momentum. This is the torque. So we can just put them. Put this equal to that, so minus L m v, and v can also be, sorry, we need to take the derivative first because this is the angular momentum. So what's the derivative of the angular momentum? So d by dt of all this stuff, L m v, and we have n Well, this is of course equal to, this is constant, the mass is constant, the derivative of the velocity is the acceleration, and we're going to write it in the following way. Lm s double dot in the n normal direction. S double dot because it moves along the circumference, and when talking this space it covers with s, so s dot is the velocity, s double dot is the acceleration. And now we notice another thing, that s equals to this arc of the circumference equals to the length times the angle. This is simple. The angle in radians, of course, this is simply basic trigonometry. So this equals to, we have an L squared, because we have L also here, and it's constant, so we can bring it out from the time derivative, and we have theta double dot in the normal direction, where double dot stands for the second derivative with respect to the parameter t, time. Now we can say that this equals to this, so minus L mg sine theta in the normal direction equals to L squared m theta double dot in the normal direction. But since we're talking about the same component, we can just remove this normal vector, because we're talking about the same component. Now we can simplify L and this L squared, m and m, and we can rearrange the equation in the following way. Theta double dot plus, we can bring this to the other side of the equation, and L to this side, so G divided by L times the sine of theta equals 0. And this is the pendulum equation. In the next video, we're going to solve this equation. And as always, don't forget to subscribe to my channel, share this video with your friends, and see you in the next video. Bye.